the last lecture we discussed about the undamped free vibration system. We already said the essential characteristics of a given system could be the mass, could be the restoring force represented by the stiffness matrix, and the resistance offered by damping C and the external agency which is f of t, out of which we already said mmk must be present for any system, C and f of t may not be present. So, if C is not present, it was considered to be an undamped system. In the last lecture we discussed about so this was the result what we had in the last lecture, where x naught and x dot naught were the initial conditions, x 0 is the displacement at t is equal to 0 and x dot is the velocity at t is equal to 0, which were the initial conditions which enabled us to find out the constants C1 and C2 in the solution of ordinary differential equation, which we solved and got the response. This was the response which we got in the last lecture. We will move on to one step further. We said now let us say mass be present, k be present, C be present, but f of t be absent. So, we will talk about damped free vibration response. Now, let us try to plot this and you will see and as I would say this is my x 0. So, it has got an initial slope. So, x dot 0 is the derivative of that, which is also present, it is not 0. And you will notice interesting phenomena in this response, that this response is not actually decaying at all. The amplitude will be constant, it will be continue for infinite number of cycles, but in reality it is not so. Any resistance offered by air, let us say by water media, in case of ocean structures, will try to reduce this response at least after n number of cycles. One cycle is from one peak to the next positive peak, this is one cycle. It can also be from one negative peak to the next negative peak, this is also one cycle. Anyway, so the amplitude will not remain constant, it will keep on decaying, and obviously the response come to 0. So, there is resistance offered by the media which is not captured in this equation, because we have not included that resistance which is offered by the media. Now, we will capture this in this model. So, my equation of motion obviously for a simple spring mass system, free body diagram, let us say this is my mass and acceleration, the restoring forces is kx and one more restoring component, because this is the resistance component offered, which will be Cx dot. Now, the question is, what are the source of damping, how many types of damping are there? Damping can come from two sources. One, it can be from the frictional resistance. which is called as Coulomb damping. The other one is coming from the hydrodynamic damping, which is viscous damping. Let us talk about the first case, which is the frictional resistance. We know that any two body, or let us say one body, is moving against another surface. Heat will be generated and the resisting force will be normal to the surface. So, that can be the resisting force can be the normal force multiplied by coefficient of friction. This is valid in our case because the normal force, which is nothing but the inertia or the mass, is very high, therefore, this resistance force will be very high. The only difficulty in this case is the dissipation of energy or the dissipation of the response or the decay of the response in this case will be very slow. So, once we derive the equation of motion for this and solve this, I will show you a comparison between the viscous damping part and the Coulomb damping part, and I will show you why in offshore structures people follow viscous damping model rather than the Coulomb damping model. It is a valid example. Okay. Now, where are they applied? Interestingly, I have a top side detail, maybe I have a template structure, maybe these are the lacings and battens. Let us look at this connection. I have one member, I have another member which is connected with an Y joint, let us say. Now, these can be either welded or bolted, etc. So, there are two material involved now. You will all agree that the material strength or the characteristic grade of steel used in this connection is far higher compared to the characteristic grade of steel used for the members, because joints or connections are subjected to high stress concentration factor in offshore structures. When two different material of different yield strength grades are attached or connected, when they rub against each other, they will offer resistance. So, this is a very valid example model applied in offshore structures where there are connections, but in the new generation structures these connections are essentially avoided. Let us take for example a TLP. There is no rigid connection in a TLP of this order. So, therefore, this model or this proposal of using Coulomb damping for expressing decay of response may not become valid for all kinds of structural models. Then what is a valid model? The second model applied or available is viscous damping. In this case, the damping force is proportional to the velocity. One can ask me a fundamental question here, why the damping force proportional to velocity will be always present in an offshore structure? We all know whether it is fixed or compliant. Considering these two, they will have very high displacement, that is why they are called compliant systems. Compliant means movement. When they have high displacement, they will have high velocity. When they have high velocity, the damping force proportional to the velocity will be very much present in the system. So, it is a very valid reason why viscous damping can be applied to ocean structures, that is first reason. Now, this damping force remove the constant proportionality equal to some constant C of x dot. We call this C as a damping coefficient. The damping coefficient now will have a force of Newton per meter per second, because this force expressed in Newton, velocity is meter per second. That is why we say the damping coefficient C will have a unit in SI as Newton per meter per second. So, the one reason is our new generation systems are designed to have high displacement, they will result in high velocity, therefore, dissipating force or the decay component of response will be significantly present because velocity of the structure will be significantly there. So, this qualifies application of viscous damping in offshore structures. The second reason, offshore structures are generally placed in a media which offers also damping, which we call hydrodynamic damping. And we all know that offshore structures without water does not exist. So, this will be always present. So, even if a structure is not moving, the water particle around the structure will move, which will cause dissipation. So, this becomes the second reason why viscous damping is comfortably recognized and recommended to be applied for ocean structures. Now, compared to these two reasons with respect to the other one, we generally prefer to have viscous damping as a dissipating force or as a resisting force in the system compared to that of Coulomb damping. So, therefore, in my system this C should be proportional to x dot. Okay. So, there are two forces now, one is the restoring force offered by the spring stiffness, so now we can write equation of motion simply mx double dot, which is the force into acceleration, Newton's law, should be given be equal to minus kx minus Ex dot. This negative indicates that the inertia force applied this way and these two are restoring. Okay. They are trying to bring it back the system to normal, that is what we call as recentering capability. There is a minus sign applied here. So, my equation of motion becomes mx double dot plus Cx dot plus Kx is 0 is my equation of motion. This equation of motion is qualifying presence of damping term, therefore, this is damped free vibration because the right hand side has got no external excitation applied to the system, it is 0. So, let us rewrite this equation x double dot plus C by m of x dot plus k by m of x as 0. So, the classical auxiliary equation d square plus C by m of d plus omega square is 0. So, it is a second order ordinary differential equation, therefore, the solution should be the roots of this equation, which will give me a complementary function will be If I say these are my roots, so they are real and distinct, therefore I can easily write my complementary function for this. But now I will pick up this argument which is the discriminant term D and try to qualify this statement depending upon the qualification of this term. For example, this term can be 0, this term can be positive, this term can be negative. Depending upon the qualification of this term, the roots will vary. For example, if the discriminant term is 0, the roots are real and equal, we have a different complementary function. If the discriminant is negative, the roots will be imaginary, you have a different complementary function, and so on and so forth. Okay? They are now classified in structural engineering as 3 different terminologies. One is what we call critical damping. Mathematically it is nothing but the discriminant is set to 0, that is this term is set to 0. Mathematically that is called critical damping. The moment I say this, so C by 2m the whole square minus omega square set to 0. So, C by 2m is set to omega square, omega. So, I should say this is CCR is 2m omega. I am using CR indicating that it is critical damping. I will call this is equation 3, I will call this is equation 4. So, equation 3 will be now modified as alpha 1 and alpha 2 both will be equal to minus ECR by 2m. I am just replacing C with the suffix CR indicating that it is a critical damping solution. Therefore, x of t for both the roots real and equal, we know it is a plus bt of e to the power of alpha t, where a and b are the constants which can be evaluated depending upon the initial condition. So, x of t can be simply a plus bt of e to the power of minus ECR by 2m equation 5. Now, let us look at this equation and try to quantify, or let us make some observations. The first observation here what we make is this response is going to decay. How? Because this term has an exponential decay term, because mathematically e power minus variable will cause decay. The second observation is this decay will be faster because it is exponentially decaying. So, the observation is if you use viscous damping, energy dissipation or response decay is exponential. Then one will ask a question inquisitively, if it is Coulomb damping, how the dissipation will look like. Okay, let us try to answer that slightly later, but take it granted it is not exponentially decaying, it is going to be linear decay, which is also physically examined. Have a platform or a moving system or a vibrating system in a body which is filled with water. when the water is vibrating around the structure, you will see that the motion of the structure will be dissipated faster. So, physically this is verified. Okay, this is verified. It suits us. There is only one part of the story where the discriminant is set to 0. There is second part of the story where the discriminant is either positive or negative. In case discriminant is negative, this is called underdamped system. In case it is positive, it is called overdamped system. Let us write down the equation for discriminant again. D is C by 2m square minus omega. That is a D term. For D to be negative, that is underdamped system, C by 2m square minus omega square is less than 0. Why? Because CCR, we already know this, we wrote it somewhere, no? So, C is less than CR, that is why it is called underdamped system. So, C by 2m omega is expressed as zeta, it is called damping ratio, always less than 1, usually expressed in percentage. 1 means 100%. How can you say it is less than 1? We already know that C is less than CCR. In offshore structures, generally is taken as 0.05 or 5%. In steel structures, it is usually taken as 0.02 or 2%. That is the usual value. Now, one may ask me a question, how this can be estimated? The only way to estimate damping coefficient is by experiments. Damping coefficients cannot be estimated analytically. You can estimate zeta only by experiments. I will show you how. So, let us come to this argument, D C by 2m the whole square minus omega square less than 0, so it is negative. this 1 by 4 factor outside, we can remove that and introduce it here in the multiplier. So, we already know C by 2m also, C by 2m is zeta omega, therefore, this can be rewritten as I square 4 omega square 2 zeta omega the whole square, I square 4 omega square minus 4 zeta square omega square, I square 4 omega square 1 minus zeta square. Now, we can write the roots alpha 1 alpha 2 as that is how this 4 has gone in. Okay. So, this will give me now minus C by 2m plus or minus I omega 1 minus zeta square. I call this term as omega d, where omega d is omega 1 minus zeta square called as vibration frequency. So, minus C by 2m plus or minus I omega d. So, real part, imaginary. So, I can write the complementary function. We can also write some observations from this result. This is going to be equation number 6. Some observations on equation 6. Equation 6 indicates response of a damped free vibration system. It also shows that the response is decaying. How? There is an e power minus term present here. The response is decaying exponentially irrespective of initial conditions, because initial conditions is now going to give me the value of A and B. Whatever may be these values, it will still decay exponentially because there is a multiplier on this. So, this will show that the response will come to 0. Okay, how many cycles that we will see, but it is going to become 0 because there is a decay. The third observation we have is the response also depends on damping. The amount of damping you give. which is nothing but a ratio. Friends, there are two ways to bring down the response. One, the exponential decay, which is related to the damping coefficient and the mass of the system. The second is give a very high damping, okay, still it will come down. The second option is not preferred in offshore structures, because damping of high value will cause damage. So, therefore, a lower value of 2%, 5% is preferred. So, this resembles a complete model of understanding that my offshore platform, after specific cycles of number of cycles in time scale, should come to 0 or recentering position, which satisfies the equation, and the response x of t shows mathematically it will decay and die down. Now, to plot this, first I would like to evaluate A and B, then for different ratios along the time scale, I want to mathematically and graphically show you how this will decay. Now, mathematically you are able to experience the equation here, but once you plot the values and say for every cycle you know how much the decay, which we call as a logarithmic decrement, mathematically it will be very interesting for you to know how this depends on z. So, first let us evaluate A and B. So, I want initial conditions. So, at t equal to 0, let x 0 and x dot 0 be initial displacement and velocity respectively. So, x of t please make a correction here, this is omega d, damped frequency. So, let us differentiate this. That is my differential. Okay. Okay. Let us now substitute the initial conditions, where x naught and x dot naught are the displacement velocity at t is equal to 0. So, let us say x 0 is this equation I am picking up, t is 0, this term goes away because it is a sine term, this becomes unity. So, it is a minus e omega t. So, x dot 0, I am applying the second equation, t becomes 0, therefore, the sine terms will go away, the cos terms will become unity and exponential powers will become all 1. So, minus zeta omega a plus omega dv. Which is minus zeta omega a is x naught plus omega d b, which gives me b is x dot 0 plus zeta omega x naught by omega d. So, I get the full solution now, which is x of t as x 0 e to the power of minus zeta omega t cos omega dt plus x dot 0 plus zeta omega x 0 by omega d sin omega dt. There is a multiplier here of e zeta omega t. What I will do is slightly rewrite this equation. Okay, now it is on. E omega t is in both cases available. So, I will pick it up and x naught is what is a cos omega dt and b is available here, which is root. Equation 7. Now, it is rather difficult for us to realize from equation 7 actually how the decay is happening. We all know that it is mathematically decaying because there is a multiplier e power minus zeta omega t available. Despite the initial conditions of x naught and x dot naught, this will decay, there is no doubt. And there is an omega d multiplier also. Omega d is nothing but omega 1 minus zeta square. If any higher value of zeta, this value will be lower and lower. So, it will cause damping, it will cause decay, no doubt. I want to plot this. Now, the variable for plotting is only t. Okay. I must select the value of t intelligently in such a manner that this function can be easily recognizable and can be plotted. So, let us say I want to plot equation 7 for understanding. Of course, if you just write this equation, give the variable in Excel, it will plot automatically for different values of t, but let us see here how manually we can do that. We know that at t is equal to 0, x is x 0, which you will get from this equation automatically. Let us say t is equal to 0, this becomes 1, this becomes x naught, this term anyway goes away because there is a multiplier of sign. We will get back this condition, right. Now, at t equals pi b omega d, this is omega suffix d, okay, it is damped vibration frequency, it is not omega d, pi b omega d. Now, when I use this here pi b omega d, possibly this omega d and omega d in the variable argument will get cancelled. I get cos and sine as multipliers of pi, which will be easy for me to recognize in the mathematical function. Okay. Now, can you give me the value for this? If you expand, substitute in here, you will see that this will become cos pi, this will become sin pi, and these values are very well established in the trigonometric functions, we know that. It is easy to find out the value of x of t. Can you give me the value? because this will become negative. So, one can say that this is going to be minus x naught e to the power of minus zeta omega by omega d of pi. So, next value at t is equal to 2 pi by omega d. Now, one can ask me a question, why I am selecting an interval of pi? We know that for a sine and cosine function, let us say a typical sine function, 0, pi by 2, pi, 3 pi by 2 and 2 pi. So, it is actually changing its sign at an interval of pi. So, I am making that interval here to see how it is actually decaying. Okay. So, let us take the next value as 2 pi, 0, pi, 2 pi, obviously 3 pi by 2, 4 pi by 2, etc. like that. I will keep on doing. Now, let us see what happens to x of t. That is what I will get. So, these are the values I am getting. Let us quickly plot these three and see what happens. The general equation 7 we already have in your printed page. We try to plot against t at every point of our interest. This is 0, this is pi, this is 2 pi and so on. At 0 I add a positive initial displacement, this is x of t. Equation 7. There is some value, I do not know this value, it is a known displacement given to the system. I think you will be able to answer this question, why do we have to give a known displacement to the system? To set initial vibration to the system we need to give this, okay. So, we are given this value, it can be negative also, does not matter, right. So, at pi it was negative, so we started from positive, at pi it became negative. Remember this value or this ordinate or this value in the graph will be much lower than this, okay. Let us mark it accordingly. If this is this way, this is slightly. Why? There is a multiplier of e power minus. Similarly, when you go to 2 pi, it becomes positive of x naught, some multiplier, it is positive, right. So, there is a cycle change, and remember this value will be much lower than this, and this is lower than this. So, there is a decay happening. So, if you try to plot come to 0, okay. So, if you join the positive amplitudes of all, you will see there is an envelope generated, this is what we call it is an exponential, it is not a linear line, it is an exponential decay. Now, one can ask me a question interestingly, how to estimate zeta from this. Now, take a spring mass system, with or without a dashpot, set a vibration to this, will come to 0, plot an accelerometer or a displacement transducer, try to capture this decrease in response experimentally. You get this plot automatically from the experiment, okay. Now, I note down these peaks, I call this as x naught, I call this as x1, I call this as x2. I can call this as x of minus 1, x of minus 2, x of minus 3 and so on. So, this negative indicates they are lower envelope, positive indicates they are upper envelope, okay. And I am not plotting this from equation 7, I am plotting this from an experiment which is directly obtained from the instrumentation, maybe accelerometer, maybe transducer. So, I get this curve. From this curve I can always read these values, whatever may be the number, right. So, it means these amplitudes be positive or negative is known to me by magnitude, I know them, okay. Once knowing this, how to get zeta? That is our question, because we are interested in knowing at what zeta this decay occurred. We did not know that because we did not model that zeta. Remember very interestingly, if you do not know zeta, you cannot plot this envelope from equation 7, see, you cannot plot. Understand the point? This is where the catch is. If you do not know zeta value, you cannot use equation 7 to plot this envelope. You have to substitute some value for zeta. Now, my idea is to obtain zeta after the envelope is obtained directly from the experiment. Okay? What is that zeta which has caused this decay? We will see in the next class. So, any questions here? Any questions? So, let us quickly summarize what we have seen. We have taken a damped vibration, free vibration system. We derived equation of motion from Newton's law, and from the free body diagram wrote the equation of motion, solved it as second order ordinary differential equation, substituted initial conditions and found out the constants and qualified x of t for two modes of damping. Of course, in this lecture we focus viscous damping. In the next lecture we will take up Coulomb damping, compare these two and see why viscous damping is effective and recommended in offshore structures. For sure we have concluded that yes, if you have a damping ratio for any value of zeta, this is exponentially decaying, which is required in the design as a form requirement of offshore structures, what we call as recentering capability of a given system. It must come to 0. Interestingly, understand, you did not start from 0, you start from x naught, but system will come to 0. This is where the problem is, okay. You need not have to start from 0, system will come back to 0, that is recentering. Recentering is not where you started, system will come back, no, system will come back to state of equilibrium. This is disturbance of equilibrium. Clear? This is what we have done, okay.